Hello and welcome. In this video, we'll be discussing how to actually conduct a one-way analysis of variance using R. Now, there were several approaches presented in the lecture notes, and we're actually going to discuss how to do all of them using R. In the future videos, we'll discuss how to do some of the components and, of course, use some of these built-in features. So we'll discuss how to do this the long way, the shorthand way, and using the built-in features in R. So we're going to do it all. We're going to do it all. To start out with, we're going to need our wide data and our long data. So this is how I entered it in the last video. These are the relevant lines. If you didn't install the package tidyr and you want to follow along, you'll need to. In fact, this needs to have quotations around it. Excuse me. If you want to run it, again, I've commented it out because I ran it on my computer in the last video, and you only have to run it once per computer. But I do need to load it up now that I'm using it, and so I'm going to run all of these lines, Control-A, Control-Enter, to get going. If you don't have this from the previous video, go on, pause, type all this out, and then you can be ready to join us. All right, so I'm going to start by doing this the longhand way. And what I mean by the longhand way is I'm going to use the definitions of each of the sums of squares to do my calculation. The sum of squares within, the sum of squares between, and the sum of squares total, or the different notation, the sum of squares error, the sum of squares treatment, and the sum of squares total. Again, we use both often, and I go back and forth, to be 100% honest with you. I apologize, it kind of sucks, but it is what it is. All right, so for my data set, I'm looking at bat.dat, so I can glance at it real quick. Remember in the last video, we discussed how we can do the dimensions, that is the rows and columns. So I can quickly check that this has 5 rows and 3 columns. And that lets me say, okay, if this has 5 rows, 3 columns, there's 15 total data points. My capital N is going to be 15. Now, when I'm doing the longhand calculation, or even some of the shorthand calculations, one of the first things I have to find is a y.bar. So I'm going to make a new variable, ydDB, and I'm going to do my calculations. Now, the sum command finds the sum of a vector, but what's cool is the sum command actually also can add up all entries in a data set. So remember, my goal is to add up all of the values in the data set and divide by the total number of values there were, the sample size. So I take all the values in the data set, divide by 15, and I get 73.8667. And I'm going to save that as the variable y.bar. As before, remember that in place of the variables, you can simply copy and paste the numbers if you prefer. That's completely fine. I mentioned that several times in the previous videos, and similar to how I stopped mentioning both notations in the middle of our lecture set, just so that we can move forward, I'm going to stop mentioning that here, but please don't forget that that's always a possibility. Of course, if you're using the built-in functions, you don't really have to worry about that through your work. But again, some of the problems can't be addressed using the built-in functions. All right, so let's think about what our sum of squares total was. Well, I took every data point and I subtracted it. So bat.dat is all of my data. And I subtracted the mean from every data point, y.bar. So I took every data point and subtracted the mean from it. Again, you can see in R how quick this is. Something like this by hand wouldn't be impossible, but it'd be a little bit of a pain, and this just happens so quickly. I'm going to copy and paste this. I'm going to highlight it and do an open parentheses to wrap it in parentheses. Of course, you can just go at the beginning and end and add a parentheses. And then I'm going to raise this to the second power. So I take the difference between each data point and the mean, and that gives me a whole bunch of difference scores. Then I square each and every one of them, and then I add them all up. So I'm going to take the sum, open parentheses, and I'm going to paste this into there. It's going to add up all of these squared difference scores, and that's my total sum of squares. So that's how I get SST, the total sum of squares. Again, doing this by hand, a big pain. Doing this in R, this is actually pretty easy in comparison to doing this by hand. All right, let's talk about the sum of squares between now. Now I'll need the variable j. Remember, j is the total number of observations in each group. So there's 5 observations in D, 5 in E, 5 in G. So j is going to be 5 observations in each group. Now I'll need the group means. We actually talked about how to do this in the previous video using the apply command. So I'll use my wide dataset, batdat, and I'm getting an error because I didn't tell it to do anything. Remember, 2 says do this command, the mean command for the columns. The option was 1, which does it for the row, 2, which does it for the columns. Anyway, in this case, I have the group means. And so I'm going to save that as a variable gr_mean for my group means. And again, this is just a list of the means. But what I want to do for each of the group means is I want to take, and the equation was take each group mean and subtract the grand mean. So I'm going to take each group mean and subtract the grand mean, which for me is y dot dot bar. Again, can I do this manually, each number minus the grand mean? Absolutely. I can write out, copy and paste the grand mean. I can take 70.8 minus this, and then I can hit enter, and that's negative 3 point blah, blah, blah. I can do that for each one. That's completely fine. I'm just not going to do that. And I promised I wasn't going to lawyer up on each of those things, so I'll stop doing that now. Now I'm going to wrap it in parentheses and raise it to the second power. So I square each of those group means minus the grand mean. That's the y dot bar. That's my group means. And this is for all of the i's. This is I equals 1, y1 dot bar, y2 dot bar, y3 dot bar. The mean for group 1, mean for group 2, mean for group 3. For each of them, I subtract the grand mean, and this is what I get. For each of them, I then square it, and then I add all of those up, sum. And then again, I just do a lot of copying and pasting because I'm in a computer and I can't copy and paste. It makes my life easy. After I copy and paste, so this is the sum, everything in the summation notation. Remember, in my equation, I had j times that sum. So I take j times the sum that I had, and this is my sum of squares b, sum of squares between. And again, I save this so that I have easy access to sum of squares between without having to rewrite that whole thing, or without having to copy and paste a number. The other thing with copying and pasting numbers is I don't always remember what the numbers represent. What's 340 versus what's, I don't know, 73 point, I just don't remember all of them. So I'm just not going to worry about it. All right. Sum of squares within. So I'll say this one's actually a little bit complicated to do in the longhand form. So you'll note that for some of these are really easy to do in the different forms. So for instance, sum of squares within in the shorthand form, we just add up the variances. That's really easy to do. But in the longhand form, this one's a bit of a pain. So in this case, what I might do is say sum of squares within plus sum of squares between equals the sum of squares total. But if I subtract sum of squares between from both sides, that would say sum of squares within equals sum of squares treatment, or sum of squares total, minus sum of squares between. So if I take the sum of squares total and subtract the sum of squares between, oh, and I didn't save my sum of squares total. I apologize. I'll rerun all that. Sum of squares total minus sum of squares between, this is my sum of squares within. That's a little simple math, just moving the sum of squares between to the other side with subtraction. So that's probably the easiest way for this one. But let's do it the long, painful way too, just so you have a copy of it, and you can do it if you want to. Don't say I never did anything for you. All right. So what we would then do is we would take the each group, bat, dat, d, minus the mean of that group, bat, dat, d. I would, that's my movement in each group. I would then square that movement. And then I would add all this up for each of the different groups, the distance between each group's data point and the mean of that group. So essentially what I'm going to do is I'm going to do this for each group. So I'm going to take the sum, and then I'm going to do this for group 1. And then I'm going to hit a comma, and I'm going to do the same thing. I'm going to paste, but now I do it for the second group. The label of the second group is E. and then I'm going to do a comma, and I'm going to do a paste, and I'm going to do it for the third group. The label for the third group is G. Y'all, do you have to do this? No. Remember, I could just do sum of squares total minus sum of squares between if I'm doing it the longhand way. And we're going to show the shorthand way in a second, so you can do that. Also notice, I'll also note, do you have to type out all these things? Y'all, absolutely not. I need to type this. I need to type n equals 15, capital N. I need to type y dot bar, and then I can go straight to sum of squares total, sum of squares between. This can be 4 lines. I'm just kind of showing y'all the work and what each of the pieces are doing here. So you don't have to show all that work if you don't want to. All right, so this is the sum of squares within right there. Yay! So I'll go on and save that. Just copy sum of squares within is, and then paste, and that's my sum of squares within. Again, even for sum of squares within, we could have found that a lot quicker with a lot less pain. So I could have n equals 15, y dot bar, SST, SSB, and then SSW equals this, and that would be all of this material here. So again, you can do it a whole lot quicker than I'm showing it in the notes. I'm showing you the pieces to explain what each of the pieces are as we write them in R. And now I have my 3 different sums of squares. And remember, that's kind of the hard part when building the tables by hand, is finding the sum of squares. So this is a relatively quick way to find sum of squares total, sum of squares between, and sum of squares within using the longhand form. And again, what is longhand by hand is actually not too difficult in R. All right. Let's show how to do the shorthand. And what you'll notice is, as I mentioned before, the longhand stuff is more complicated for some things, like the sum of squares within, if I did it the longhand formula way, is a little more complicated. But the sum of squares between and sum of squares total was pretty simple. And the sum of squares within, once I had those two, was pretty simple. Shorthand, and again, all of these longhand, if I did it on paper and pencil, would be a huge pain in the butt. But shorthand, which would normally be easier, remember that shorthand for the sum of squares total was kind of a pain. There wasn't really a nice way to do that. Well, shorthand, the sum of squares between, sum of squares within, those are going to be easier here in R, but the sum of squares total shorthand equation is going to be a bit of a pain. All right, so I've got my group means, I've got my y dot bar. Now, shorthand, remember how we could find y dot bar. Now, I already have y dot bar saved, but if I wanted to find this in the shorthand, we said we're going to find the group means. So I'd take the group means and copy and paste that down here, and I would add up the group means, and I would divide by how many group means I had. I could divide by 3, or I could ask length of the group mean variable. That is, how many group means do you have? And I had 3 group means. So sum of the group means divided by the number of group means you have. And that gives me my y dot bar. So I could run that. Oh, excuse me. I could run that, or I could run y dot bar. And again, we already found y dot bar, so I'm not going to re-save that here. But if I was doing this using the shorthand equation for y dot bar, that's what that would be. I'm going to change my notation just to get us some practice with a different notation. Up here it was SSB. Down here it'll be SSTR, the sum of squares treatment. And down here I'm going to save the sum of squares total for the end. All right. So let's see, sum of squares treatment. Again, we start with J is 5. I take the group mean minus the grand mean, y dot bar. So remember previously, I took the, I guess previously we did the same thing, group mean minus the grand mean, and then divided by, so all this, now that I'm looking at it, all this is exactly the same, isn't it? So the shortcut for the sum of squares between is kind of the same stuff. The group mean minus the grand mean, square it, and then multiply that by J. So let's see. Oh, excuse me, add it all up. Nope, I copied the wrong thing. Control Z to undo. I need to copy the squared stuff, add up all the squared stuff, and then multiply that one. Yikes, messing up my copy and paste. J times that stuff. That gives me my sum of squares treatment. And again, I can just go up, check that sum of squares between, make sure that those came out the same. Perfect. All right. The more fun one, remember sum of squares within up here was kind of a pain, but sum of squares within down here, and again, I'm just changing the notation, sum of squares E, but these are the same number, same quantity. It's just some people use SSW, some people use SSE. Here, I'm going to make the group variances. So I'm going to do that same apply command, and I'm just going to go up and copy and paste where I use that apply command. Here it is, apply. Just going to copy and paste that whole line. So this is where I made the group mean vector, that it was all of the group means in a single place. Here, instead of the means, I want it to be the variances. So I'm going to rename the variable gr_var for group variances, and I'm going to do the apply command, but now for each column, I want to calculate the variances. So instead of each column giving me the means now I'm going to have the variances associated with each group. Group variances. Sweet. All right. Now for the shortcut way, I just add up the group variances. And then I multiply times j minus 1. So I'm going to copy and paste. Now remember j minus 1 in parentheses times the sum of the group variances. And if I go look at my sum of squares within from previously, this is exactly the same thing as I'm calculating here. Again, sum of squares within, sum of squares between, same notation, but like I'm just confirming, this is all that was needed to calculate that quantity. J minus 1 times the sum of the group variances. Again, the hard part, if you're doing this on paper and pencil, is calculating all these variances. But I quickly add them up, multiply by that j minus 1, and that gives me my sum of squares for the error. I guess because I'm using different notation, I didn't save this one as my different notations as SSTR up here. I'll just go on and save that as my different notation. And run all these to make sure I didn't miss anything. All right, so now down here, let's go on and do my sum of squares total. Now remember, I can do the SS treatment plus SSE, and that gives me the sum of squares total. If I go up and look at my previous sum of squares total, this is what my value is, 619.733. So this works. I can do that. Again, I have, say, SSB and SSW are the same thing. This also works up here. So either of these work just fine once I have those. And again, this version of the sum of squares error / sum of squares within, whichever, is much easier to do, quote unquote, by hand in R than this one up here. It kind of depends on what data format you have, but this one's just way easier, I think. Sum of squares between / sum of squares treatment, these are calculated the same. The sum of squares total, this one I think is pretty easy, but you know, if we're doing the calculation for sum of squares total, honestly, it's not too bad. I need my capital N. I already mentioned that's 15. I can look at the dimensions of my wide data and see what that is. In the long data, it's the length of the long data. That's your total number of observations. But in your wide data, it's the number of rows times the number of columns. And then my equation is, I want to take all of the data, this is the first part, that, and I want to raise it to the second power, and then I want to add them all up, sum of all of the individual data points squared. And then I want to subtract, and it's a fraction. On the numerator, or excuse me, I'll go and write the denominator, that fraction's over n. And in the numerator, I want to add up all the data. And I want you to be careful about these parentheses here because they're important. Here, I'm squaring inside of the sum parentheses. That says take the square of the numbers and then add them up after squaring them. Here, I'm squaring outside of the parentheses. That says add them all up and then square that number. And it's worth mentioning, mathematically, these are two different concepts. So we won't go into our high school algebra here, but just realize these are two different numbers. This first one, we square the data before we add. The second one, we add, and then we square the data. In this case, we get 619.7333, which matches what our previous sum of squares total was. Our previous sum of squares total was also 619.733. So this works. Again, both of them equivalent. I don't think it particularly matters one way or the other as to how you approach this. I think both of these are pretty easy. So all this to say, doing this by hand, sum of squares treatment / sum of squares between. Both of these are the same method. Sum of squares error / sum of squares within. This one, where you add up the variances, the shorthand way, seems to me to be a little bit easier if you're building out the pieces. But this is how you would build the pieces in the longhand way if you wanted to. And then sum of squares total. I think both of these are pretty easy. The sum of squares total up here, where you just take each data point minus the grand mean, then you square it, and then you sum it up. So you sum up the squared values, or you just sum up the squared outcome values and then add them, and then you sum the squared outcome values, or excuse me, sum the outcome values and then square after you sum them up, and then you divide by n, and then you subtract those two numbers. I think both of those are pretty straightforward, the shorthand way and the longhand way. All right, so that's all of the different sum of squares pieces. Those are the hard ones. Let's talk about building out the ANOVA table. And again, we're still in the by hand section here, so we'll just use these pieces above in our building out. Again, you can use a TR/E, or you can use B/W. Both are fine, and actually for me, I built both variables. You don't have to do that. Pick a notation that works for you and just realize both exist. All right, so for me, I'm going to look at my data set one more time. The first thing that I'm going to do is I'm going to list out capital I and capital J. That is the total number of the total number of groups and the total number of observations within each group. I already listed capital J earlier, but I'm just going to do this to keep mental track, or to keep track in the software, I guess I should say, of which values are which, because capital I and capital J are going to be involved in our formulas eventually. So capital I, 3 total groups. Capital J, we have 5 observations within each group. Capital N is capital I times capital J. That's our total number of observations, which is 15. And again, we just kind of looked at it and saw 15 earlier. But that's where that's coming from. Once I have these, I can do my degrees of freedom. So the degrees of freedom should I use B or TR? I don't know. I'll just use TR, I guess. The degrees of freedom for the treatment row is I-1. The degrees of freedom for the error is I times parentheses J-1. So remember, J-1 here is going to be 4. So I take 3 times 5-1, and I do the 5-1 first. And then the degrees of freedom for the total is I times J without parentheses -1. And that gives me 14. So I'll run these 3 real quick. And again, if you prefer to just type in these numbers when appropriate, that's just fine. It's completely up to you. I'm saving these as the variables TFTR, DFE, and DFT. And that way, when I'm reading my notes and the formula said use the degrees of freedom for the treatment, I don't have to remember what that number is. I can just put DFTR, DFTR, and that automatically gives me the right number. I don't have to think about it too much. And I like that. All right, so let's go on and calculate the mean squares. So remember, for the mean squares, it's just the sum of squares divided by its respective degrees of freedom. And we only do this for the treatment and the error. So, and then eventually with 2 samples, we'll do it with more. But for us, we're only doing this with treatment and the error. And I guess with 2 samples, we're not going to be doing this by hand anyway, so don't worry about it. All right, so for the mean squares treatment, I'll take the sum of squares treatment divided by the degrees of freedom for the treatment. So make sure you have both of these. If you haven't made SSTR yet, SSB is the one we made first, and that would go in there. Again, these are the same number, just different notations for the same number. All right, I'm stopping lawyering up. I promise. I promise. You got it. I know. STR is that quantity. And again, I'm just going to save that for later. And then my error, SSE over DFE. And then I'm going to save that as the MSE. And we'll talk about the MSE when we get to correlation and regression too. All right, so that's my mean squares. Now I have enough to calculate my F. Again, I don't find the mean squares of the total. So for the F value, I'll take the mean squares treatment over the mean squares error, and you know the other conversion, and this is my F test statistic. So I could write TS equals that, or just F equals that. So if you prefer TS for the test statistic here, that's just fine. I'll just use F for my notation here. And again, F is just that number, that F test statistic. So here I can quickly find the critical value if I want. Critical value. So for the critical value, I'd look in the F distribution, QF, open parentheses. I'd give it my alpha. I didn't make a variable for alpha. I guess I'll just hand type it 0.05. It's important to realize this is the overall alpha problem, not an alpha over 2. So if my alpha was 0.05, I'd type 0.05 into here and leave it. Degrees of freedom 1 is always going to be the degrees of freedom treatment / degrees of freedom between. Degrees of freedom 2 is always going to be the degrees of freedom error. And I want my lower dot tail equals false. This is going to be a quote unquote upper tail test. Again, it's not really phrased like that, but this is going to be putting the area in the upper tail always. And that's my critical value. So comparing F to my critical value, F is in the critical shaded region. It's in the absurd region. That is your null hypothesis, your default belief that none of the groups are different. The data is absurd when compared to that belief. And so we reject that belief. We change our mind. So we came in believing nothing's going on. All the battery lives are the same. And this provides evidence that there is a statistically significant difference between the battery lives. Practically significant? I don't know, but it's statistically significant. That means we can determine that it's more than chance. And again, the difference is not the right place to talk about it, but statistically significant says it's due to more than chance. Practically significant says, yeah, okay, but is that worth worrying about? So those are different concepts. P-value. Practical significance is kind of in the eye of the beholder a little bit. All right, so for the p-value, I give it my test statistic. In this case, I've called mine F. If you called yours what we have in the previous lectures, it'd be TS, and you'd put that there. I give it my same degrees of freedom. DF1 is DFTR. Again, that's the numerator in the fraction. DF2 is DFE, again, the denominator. And I won't say degrees of freedom between, degrees of freedom within, that's the same thing. Lower dot tail equals false. And this is my p-value. So I compare this p-value with alpha. My alpha in this case was 0.05. This p-value is below alpha. And so we determine that there is a statistically significant difference between the groups. Again, the p-value intuitively is kind of like, and this isn't technically correct, but intuitively is kind of like, what's the probability of the null hypothesis? So in this case, very unlikely. So because the null hypothesis is very unlikely, we would not stick with it. Actually, I think technically, that's the intuitive. I think technically we probably could say the p-value is the alignment, level of alignment, or a measure of alignment between the data and the null hypothesis. So this indicates very low alignment between them. I think that we could reasonably say. And now the part you've all been waiting for. So if you're given raw data, of course, you can use the built-in tests in R. There's a few different ones, but this test is going to involve 2 stages. So first of all, it's going to require our long data. And I mentioned we need the long data form to do built-in tests. So for the built-in test, we'll do AOV, that's the command, analysis of variance. Now I need to tell it which of the variables in the data set is my dependent variable and which one is my independent variable. So what I'm saying here is I think the hours depend on the battery brands. So I think that battery length depends on the battery brands is the whole thing we're looking at here. So I give it my dependent variable first, hours, and then I type a squiggle, and then I type my independent variable column name. So again, I give it the number variable, squiggle, and then the categories in ANOVA, or the dependent variable, squiggle, the independent variable in terms of our study design. Then I add a comma equals because I have to tell it which data set this information is coming from. This is coming from the LDAT data set. Now we can see that this gives us an output, and this output is fine, it's usable, but it's not particularly grand. So here's what I'm going to do. I'm going to save this. I'll call it ANOVA model. I'm going to save my AOV command. And then what I'm going to do is I'm going to use a second command to give me a more typical ANOVA table. I'm going to use the summary command. So I'll do summary. I'll put my ANOVA model into the summary command, and now I see a more traditional ANOVA table. I'll note, compared to the one that we do in class, R switches the order of the degrees of freedom and sum of squares columns, so degrees of freedom come first. But these degrees of freedom, sums of squares, mean squares, F value, and P value all should line up exactly with what we found. So I can check a few. Let's do the degrees of freedom of the treatment. That's this one here, 2 degrees of freedom for the error. The sum of squares treatment, that matches here. The sum of squares error matches down here. R calls it residuals instead of error. We'll talk a little bit about that when we get to regression. The mean squares treatment and the mean squares error. And again, all this is just matching perfectly. Thank goodness, because if it didn't, I'd have to go back and re-record that video and I would be so sad. Our P value is 0.08. 29, perfect. So all of this matches identically with what we had. Now I will mention R does not provide the sum of squares total or the degrees of freedom total. So if you want those, you'll either have to manually add these for yourself, or you'll have to go and use some of the methods that we showed you in the shorthand or longhand way to find them on your own. In this video, we've presented how we can perform a one-way analysis of variance in the shorthand method presented in the notes, in the longhand method presented in the notes, and also using built-in commands in R. Thanks for sticking with me through this video, and I'll look forward to catching you on the next one.